In this walkthrough, you'll turn your iPad into a seismometer or a mini earthquake detector. As you can see, there are 3 different ways to view the motion data: needle, graph, and bubble. Let's tap the information bubble in the top right corner of the app preview to learn more about the sensors in the iPad. Your iPad is equipped with a gyroscope and accelerometer. In this walkthrough, it'll be reacting to the information received by these hardware sensors, not just button taps or user input. The first thing we'll do is set up a way to read the detection data, and the first thing we'll set it up for is our device's yaw. Pause the video and try moving your iPad to see if you can determine what the value ranges for yaw are. As the pop-up says, yaw represents the rotation around the center point of your device and is kind of like using the steering wheel of a car. So let's expound on that analogy a little bit. Why is the value range of yaw negative pi to pi radians? Pi comes up a lot in math when we deal with circles, and it's essentially just the ratio of a circle's circumference to its diameter. And steering wheels are circles, so if we think about yaw in terms of the steering wheel or car analogy, then we can see that it makes sense for the range to be negative pi to pi. A counterclockwise turn will be represented by 0 to pi, and a clockwise turn will be represented by 0 to negative pi. But our world is 3-dimensional, and so there are also other values that we need to measure in addition to yaw, and this is where it's helpful that the gyroscope also measures pitch and roll. But in addition to storing data about how our iPad is positioned, we might also want to know how fast it's moving, and this is where the accelerometer comes in. Go ahead and add these lines of code to see the accelerometer data. Much like a library, for this project we're using the Core Motion framework, which is how we access, manipulate, and turn all of the cool motion data into neat projects. So you can see the documentation here, which lists all sorts of different other things you could use it for. For example, a pedometer if you wanted to track steps using your iPad's motion sensors. But I wouldn't suggest these water submersion ones for your iPad. Leave those to something waterproof. Now, so far we've been reading our data just using numbers, but wouldn't it be so much more fun to visualize it using shapes and colors? Go ahead and add a rectangle to your code. Alright, now instead of this big plain blob, let's add a little bit more code to style and simplify it. As you can see, we're also doing just a little bit of math in this code in order to make our rectangle change with movement, or change based on the new numbers, the new data. And here's what that math looks like written out instead of just in code. So roll's range is also negative pi to pi, and the problem with that is our user interface can't really use negative values to manipulate the size of the square. So before we do anything else, we need to shift the roll value into the positives by adding pi to whatever it is. And we'll account for this by dividing by 2 pi after that. So let's say that the roll value was initially negative pi and our iPad was turned all the way in one direction, and then we added pi to it. Negative pi plus pi would just be 0, and then we divide 0 by 2 pi, which is still 0. So instead of having negative pi as our far end number for that side, it will instead be 0. And this will make flat 0.5, and it will make the opposite direction 1. So all of our values remain positive, and we can make a cool rectangle. And then the purpose of multiplying by 300 is just to scale the number that we get to the size of the screen to a number of pixels that makes sense for our visualization, because, for example, a 1 pixel rectangle would be kind of hard to see. Here we'll go through a similar process for a second rectangle. As you can see, this rectangle's angle is changing rather than its size. And if we add this modifier right here, we can make it do some flips. We can make it 3-dimensional. Now let's try making the color dependent on the data. This is cool, but it would probably be more helpful and informative if we had it change based on the direction. So it goes red in one direction and blue in another. Now's a great time to pause the video and get creative. Maybe you want to make some circles or rectangles that their color is changed by the accelerometer data, and their size is changed by the roll data, and maybe their angle is changed by the pitch data. Just tinker with it and have a good time. Alright, now let's try changing the color of the needle based on the strength of the vibration. To do this, we'll map the z acceleration to the angle of the needle rotation. The needle is just a rectangle, which we already know how to customize, so we can change its color by just setting it up to be dependent on that z acceleration value. That definitely looks cool, but it's too colorful to be informative, so let's narrow it down in a way that makes sense. Much like the way we made our rectangles turn red in one direction and blue in another, we'll have the needle change to be blue in one direction and orange in the other. And for this, we'll need to use a ternary conditional operator. With this operator, first we'll check our condition, in this case whether or not the z acceleration is greater than 0.3, and if it is, then our true value is orange, and if not, our false value is blue. And we'll want to mirror this change on the base of the needle, the little circle at the bottom as well. Alright, now let's turn to the bubble view, which shows us how level or not level our iPad is. The roll and pitch data are converted into x and y values, and the closer that they get to 0, 0 or the center, then the more level the iPad is. The prompt asks, can you think of another way to use the data to show how close to the level you are? Maybe the bubble circle can get smaller as it moves away. Before we do so, it'll be helpful to add these lines of code, which will show the x and y coordinates as the bubble moves. There are multiple ways you could make the bubble size change as it moves further and closer to the level, but I'll just cycle through a few different ones here. Note that these probably aren't the best solutions, they're just a few. And lastly, here's the solution that's provided by Swift Playgrounds. We might also want to add some kind of alert that lets us know when it is level. In this case, we'll add a party hat emoji. This is just a simple if statement checking whether our x position and our y position are within a certain range, and then when they are, we display the party hat. So far we've seen how to visualize data in a moment, but we might want to be able to visualize a long history of data so that we can notice trends and patterns. In order to do this, we'll need to start storing our data, and one good method of storing data is to use an array. If you're not familiar with arrays, check out the glossary on our website. Keep in mind that as long as the app is running, the motion sensors are going to keep providing data. As you can see, the pitch data on the side of the screen keeps changing. So if we don't set some kind of limit for how much data we want to store at any given time, it's going to get very big and very unmanageable very fast. So we'll make a variable right away called max data, and you can set it to anything. We'll set it to 20 for now, and that will be the max number of values that we keep in our array at a given time. And we'll use onUpdate and onAppear to manage how we track the data. So now we need to write code that actually adds the new data to the array, and each time that we do so, we want to make sure that we're not over that max capacity that we've set up, max data variable, and then if we are, we'll want to go ahead and drop the oldest data so that we have room for new. Next, we'll need to be constantly iterating through the array, seeing what the new data is, and displaying it. For this display, let's use some circles, and let's have their position change according to the data. Now is a good time to pause again and just try to play around with different aspects of this code, maybe switch VStack to HStack, or change the scaling factor, maybe play with the color of the circles. For example, one thing you could try is updating the color of the circles according to the pitch data. Now we'll take a look at our line graph. The x-axis represents time, and the y-axis represents the vibrations. Just like we set up a maximum amount of data with our previous array, we'll need to do that again here, but we'll set it to a higher value this time. Let's start with 500. Now let's see what happens if we update it to 1000. As you can see, the line moves much slower because it takes more time to gather 1000 pieces of data than it does 500. Let's change it again, but this time to 10. Now the graph is really hard to read because 10 pieces of data come and go so quickly that it basically just looks like a wiggly little line and we can't notice any trends or patterns. It's too zoomed in. So we'll take a look at how the data is added to the array. So all of this is on up here when the screen is opened. As we record data, we continuously append the z acceleration data to the end of that array. And if at any point the number of data points that we have is larger than the capacity, than the limit that we've set up with our max data variable, whether that's 500 or 1000 or 10, we'll go ahead and drop the first data point so that we can make room for a new one. For this next step, we'll be including the charts framework, which again is like including a library in Python or C++, and you can see our glossary video for that. We still want the x-axis to represent time and the y-axis to represent our z acceleration data. With our array, we add new data points to the end and remove old ones from the beginning as we run out of space. So for our x-axis, where it represents time, we'll be using the indices, and for our y-axis, where it represents the actual data, we'll be using the values stored at those indices. And this can also be customized as is explained here. Now's a good time to pause and explore this section of code by commenting out different pieces to see what they do. Just like the other examples, you can also change the color of this, and if you wanted to, you could make it dependent on the data as well. Here we'll set up the motion browser, which is going to act as a manager for all of the motion data in the app. Instead of every little tool that we make pulling in motion data on its own, we're going to have it centralized to be handled by the motion browser and then be passed on to wherever it needs to go. And we do need to decide how often to update that data. We'll set it here to 0.01 with update interval, but you can change that and see how the different visuals change in response. And now that we've created this detector tool, we want to make it available across our entire project. Now we could just pass our detector to each view, but doing this would be less organized and less efficient, and as programmers, it's our priority to make things the best way instead of just a functional way. Here on appear and on disappear and the start and stop functions are doing crucial work by making sure that all of this starts and stops when the app opens and closes. We don't want to leave anything running in the background. Now, if you want to use any of the things that you've learned here in your own app or project, you'll need to familiarize yourself with the Core Motion framework. Just Google Core Motion Swift and read their documentation, see what's available, what all you can do with it, and get started. Here, Swift Playgrounds goes through a few important syntax details to keep in mind when you make your own projects. If you're not familiar with syntax, you can check out our glossary video on that as well. Now, just like we created a detector tool, let's go ahead and create a timer tool. This is going to be useful to us here because we'll need to regularly update the data that's coming in, but we want to do it on a consistent interval. And we're using the keyword weak self here as a sort of safeguard for later. We want to be able to clean up everything at the end, kind of like throwing away a soda can after you drink the soda. Now here, you could add or change this if you wanted to. With our app, as we get new information, we are just updating the information. We don't change the structure of the app or anything, but if you wanted to, you could put some code in these curly braces, and every time it updated, it would change accordingly. And here's what our update motion data function looks like. As it updates, it sends out all of its new information to all of our published properties. And if there's no motion data coming in, then there's nothing to update, so it will skip this. So I had mentioned cleanup a little bit earlier when we talked about the weak self keyword, but this right here, the stop function, this is where it really happens. So we wouldn't normally need to do this step manually, but where we made the detector and timer instances, we do now have to clean them up manually as well. If we skip this step, we could continuously be draining battery and using memory unnecessarily, even after our app's need for these tools has finished. So it's an important step, and with that, we have finished our seismometer. So thank you for watching, and feel free to check out any glossary terms on our website if you need to.